Welcome to this problem-solving session. Today, we'll be tackling LeetCode problem number 2122, recover the original array. In this problem, we'll reverse engineer a given array to deduce the original array it was derived from. Let's dive in and explore the solution step by step. In this problem, we are given an integer array called nums. This array was created by taking another array, called original, and performing a specific transformation. First, an unknown integer k is added to each element of the original array to create a new array, which we call transformed. Then, the original array is concatenated with the transformed array to form nums. For example, if original is 1, 2, and k is 3, adding 3 to each element of original results in transformed equals 4, 5. Concatenating these two gives nums equals 1, 2, 4, 5. Your task is to determine the original array from the given nums. If it's not possible to recover such an array, you should return an empty array. To help clarify, let's look at an example. Suppose nums is 2, 10, 6, 4, 8, 12. The expected output is 2, 4, 6. Here's why. If we assume the original array is 2, 4, 6, and add k equals 4 to each element, we get 6, 8, 10 as the transformed array. Concatenating 2, 4, 6 with 6, 8, 10 indeed gives 2, 10, 6, 4, 8, 12, which matches the input. Now, consider another example where nums is 1, 1, 3, 3. In this case, there is no valid value of k that allows us to split nums into original and transformed, so the output is an empty array. Next, let's consider a simpler case where nums is 5, 435. Here, the array is too small to form both original and transformed, so the output is also an empty array. Now, let's review some constraints. First, nums must have an even length, as it is the result of concatenating two arrays of equal size. Additionally, the size of original, denoted as n, must be at least 1 but no larger than 100,000. Each element in nums is guaranteed to be a positive integer, ranging from 1 to 1 billion. As for edge cases, if nums has fewer than 4 elements, it cannot possibly form valid original and transformed arrays. Other edge cases include scenarios where all elements in nums are identical. In such cases, it's important to ensure that the value of k is positive. Additionally, if k turns out to be 0, the array cannot be split into two distinct parts, so no valid original array exists. Finally, we must also consider cases where the elements of nums are very large. Since the constraints allow values as high as 1 billion, it's essential to ensure that the solution is efficient and can handle these large inputs within a reasonable time frame. These considerations will help us design a robust solution to the problem. To solve problem number 2122, recover the original array, we need to reverse engineer the transformation that created the given nums array. The goal is to deduce the original array original and the integer k, which represents the difference between the two concatenated halves of original. One approach we can consider is the brute force method. Here, the intuition is to iterate over all possible values of k and attempt to reconstruct the array original by splitting nums into two halves. For each value of k, we check if subtracting k from the second half of nums produces the first half. If this validation holds true, we've found a valid k and can extract original. However, this method has a significant drawback. It requires iterating over all possible values of k and performing a validation check for each, resulting in a time complexity of n squared. While this approach is straightforward to implement, it is not computationally efficient and struggles to handle large inputs effectively. Now, let's explore a more optimized strategy using sorting and the two-pointer technique. The key insight here is recognizing that the nums array is formed by concatenating two identical copies of original, and the difference between corresponding elements in the two halves is exactly k. This observation allows us to use sorting to simplify the problem. First, we sort the nums array, which ensures that the relative order of elements is preserved. Then, we iterate over possible values of k by examining the differences between pairs of elements in the sorted array. Specifically, for a pair of indices I and j where j greater than I, the difference nums, j, nums, I, gives a candidate for k. To validate this candidate, we use a two-pointer technique to check whether subtracting k from the second half of nums matches the first half. If the validation succeeds, we can reconstruct the original array with confidence. This approach is significantly more efficient than brute force. Sorting takes O, n log n, and validating each candidate for k with the two-pointer method takes O, n, giving an overall complexity of O, n log n plus n squared. While the validation step can still be a bottleneck for very large inputs, this method drastically reduces unnecessary computations compared to the brute force approach. The optimized approach using sorting and two pointers is the preferred strategy for solving this problem because it strikes a balance between efficiency and clarity. The critical insight here is recognizing that the sorted differences between elements in nums can be used to deduce k. By leveraging the structure of nums, two concatenated copies of original, we can efficiently validate potential values of k without resorting to exhaustive search. This strategy avoids redundant calculations and ensures correctness. The key realization, or the aha moment, lies in shifting the focus from directly reconstructing original to analyzing the relationships between elements in the sorted array. This insight simplifies the problem significantly and makes the two-pointer approach an elegant and practical solution. When comparing the different strategies, each has its own trade-offs. The brute force method is simple to understand and implement but suffers from poor scalability due to its O, n squared, time complexity. This makes it unsuitable for large inputs. The optimized approach, which combines sorting and two-pointer validation, is more efficient. Sorting reduces the search space, and the two-pointer technique avoids redundant computations, making it a robust solution that performs well even for larger arrays. An alternative approach could involve using hashing to validate potential values of k. While this might seem promising, managing hash table operations and handling collisions introduces additional overhead, which can make the implementation more complex than the two-pointer method. Ultimately, the optimized approach stands out as the best fit for this problem. Its balance of efficiency, simplicity, and clear logic makes it the ideal choice to recover the original array efficiently and accurately. In this problem, we are tasked with recovering the original array, original, and the integer k that was used to create the sorted array nums. The transformation involves adding and subtracting k from each element in original to form nums, which is then sorted in ascending order. To solve this, we need to reverse this process. A key observation here is that every element in original creates two corresponding values in the transformed nums, separated by k. For example, if an element in original is x, the corresponding values in nums would be x plus k and x, k. This relationship allows us to deduce possible values of k by analyzing the differences between pairs of elements in nums. Additionally, since k must be a positive integer and divide the difference between two numbers in nums, we can generate candidate k values by iterating over all pairs, nums, I, nums, j, and calculating, nums, j, nums, I/2. To efficiently validate these candidates, we use a hash map or set to track pairs and ensure that the deduced array matches the given constraints. To solve the problem systematically, we first ensure that nums is sorted. Sorting allows us to find valid pairs and compute potential k values more easily. Next, we generate candidate values for k by iterating over all pairs of elements in nums where the second element is strictly greater than the first. For each pair, nums, I, nums, j, we calculate k as nums, j, nums, I/2, ensuring that k is a positive integer. We also store these candidate k values in a set to avoid duplicates. Once we have the candidate k values, we validate each one by attempting to reconstruct the original array. Starting with the smallest element in nums, which corresponds to the smallest value in original, we iteratively match pairs, x, x plus k, in nums and add the corresponding values to original. This process involves using a hash set to track unmatched elements in nums and ensure efficient validation. If we can match all elements in nums without violating the constraints, we store the reconstructed array as a valid solution. When a candidate k successfully reconstructs the array, we return the first valid original array. If multiple solutions are possible and required, we can store all valid arrays instead. To achieve efficient pair matching, we rely on a hash set, which allows us to check for elements in constant time. The reconstructed array is stored in a list, which simplifies the process of appending elements. In terms of complexity, generating candidate k values involves iterating over all pairs of elements in nums, leading to a time complexity of O(n squared). Validating each candidate k involves scanning nums and matching pairs, which is O(n) per candidate. Combining these steps results in an overall time complexity of O(n squared). The space complexity is O(n) due to the hash set used for tracking elements. Key edge cases to consider include very small input sizes, arrays where all elements are identical, and large values in nums that might risk integer overflow. Finally, the pseudocode outlines the recovery process, starting with sorting nums, generating candidate k values, and validating each candidate to reconstruct original. The pseudocode continues with the validation process for each candidate k. If k is positive and the difference between the pair nums, j, nums, 0 is even, we proceed to reconstruct the original array. We initialize an empty list for original and a hash set to track elements that have already been used. For each element x in nums, if it has not been used, we check whether x plus 2k exists in nums. If it does, we add x plus k to the original array and mark both x and x plus 2k as used. This ensures that all elements are matched in pairs and no element is reused. If the length of original matches half the size of nums, we return the reconstructed array as a valid solution. If no valid array is found after processing all candidates, we return an empty list. This approach ensures that we systematically explore all possibilities while maintaining efficiency through the use of hashing and pairwise matching. Here, we begin by importing the counter class from the collections module. This will help us efficiently count the frequency of elements in the array. Inside the solution class, we define the function recoverArray, which takes a list of integers, nums, as input. The first step is to sort the array in ascending order to ensure we can analyze the differences between consecutive elements systematically. Next, we define an inner function, is_valid_k, which will determine if a given value of k can be used to reconstruct the original array. The function starts by checking if k is less than or equal to 0, in which case it immediately returns false since k must be positive. We then create a counter object to store the frequency of each number in the sorted array and initialize an empty list called original, which will hold the potential elements of the original array. The core of this function is a loop that iterates through each number in the input array. For each number, if its frequency in the counter is 0, we skip it. Otherwise, we check if the number plus k exists in the counter with a non-zero frequency. If not, this means the current k is invalid, and we return false. Otherwise, we calculate the midpoint, which is number plus k //2, appended to the original list, and decrement the counts for both the current number and its pair. If the loop completes without issues, the function returns the original list as a valid reconstruction of the array. Now, back in the recoverArray function, we iterate through the sorted nums starting from the second element. For each index I, we calculate k as the difference between the current element, nums, I, and the first element, nums, 0. This difference represents a potential value for k that could lead to the reconstruction of the original array. We pass this k value to the is_valid_k function. If is_valid_k returns a non-empty list, it means we've successfully reconstructed the original array, so we immediately return this list. If no valid k is found after examining all possible differences, the function concludes by returning an empty list, indicating that it's not possible to recover the original array. This approach systematically tests potential values for k and ensures that the solution is both efficient and correct, leveraging sorting and the counter class to minimize redundant computations. Here, we begin by importing the necessary libraries and defining our solution class. The main method, recoverArray, is tasked with reconstructing the original array. First, we sort the input array, nums, in ascending order. This ensures that any derived differences between elements are calculated correctly. Next, we iterate through the sorted array starting from the second element. For each element, we calculate the difference, k, between the current element and the first element. Since k represents twice the difference between original numbers in the array, it's crucial to ensure that k is both positive and even. If it isn't, we skip to the next iteration. Now, within this loop, we call a helper function, isValidK, passing the current value of k in the sorted nums array. If the helper function returns a non-null array, it means we've successfully reconstructed the original array, and we return it immediately. If no valid array is found in all iterations, we return an empty array as the default result. The helper method isValidK is designed to validate whether a given k could generate the original array. First, we build a frequency map, counter, to track occurrences of each number in the input nums array. This helps us manage the pairing process efficiently. We then initialize an array, original, which will hold the reconstructed values, and an index variable to track positions. For each number in nums, we check if it still has a count left in the frequency map. If not, we move to the next number. The target value, which is the current number plus k, must also have a count greater than 0 in the map. If the target isn't valid, we return null since k cannot produce a valid pairing. If the pairing is valid, we calculate the midpoint value by adding k/2 to the current number and store it in the original array. Finally, we decrement the counts for both the current number and the target in the frequency map to reflect that these values have been used. Once all numbers have been processed, we return the reconstructed original array. Here, we are tasked with recovering the original array from the given input nums equals 1, 3, 4, 6. The array nums is a combination of all elements from the original array paired with their doubles, with some offset k. The first step is to sort the array to make it easier to match smaller numbers with their corresponding larger values. Since the array is already sorted as 1, 3, 4, 6, no further changes are needed here. Next, we try possible values for k, which must be a positive difference between two distinct elements in nums. Starting with I equals 1, we calculate k as nums 1, nums 0, which gives 3, 1 equals 2. This value of k will now be tested to see if it can produce a valid original array. To validate k equals 2, we use the function is_valid_k, k. First, we initialize a counter to keep track of the frequency of each element in nums, which is counter 1, 1, 3, 1, 4, 1, 6, 1. We also initialize an empty list original to store the reconstructed original array. We then process each element in nums. Starting with number equals 1, we check if it and its paired element, 1 plus k equals 3, are available in the counter. Since both are present, we add 1 plus k//2 equals 2 to original and update the counter, reducing the counts of 1 and 3. The counter becomes counter 4, 1, 6, 1, 1 o'clock, 3 o'clock. Next, for number equals 3, we skip it because its count is now 0. For number equals 4, we check if it and its paired element, 4 plus k equals 6, are available. Both are valid, so we add 4 plus k//2 equals 5 to original and update the counter again. The counter now becomes counter 1 o'clock, 3 o'clock, 4 o'clock, 6 o'clock. Finally, we skip any remaining elements with 0 counts. At this point, original contains 2, 5. With original equals 2, 5, we have successfully reconstructed the original array for k equals 2. This is returned as the final output for this example. Now, let's move on to another example where the input nums is 2, 4, 6, 8, 10. Similar to before, we start by sorting the array, though it is already sorted as 2, 4, 6, 8, 10. Then, we try possible values for k. Using the first two distinct elements, nums 1, nums 0, we calculate k as 4, 2 equals 2. This value of k will be tested to see if it produces a valid original array. To validate k equals 2 for this example, we initialize the counter as counter 2, 1, 4, 1, 6, 1, 8, 1, 10, 1, and an empty list original. We process the elements in nums one by one. Starting with number equals 2, we check if it and its pair, 2 plus k equals 4, are available in the counter. Both are present, so we add 2 plus k//2 equals 3 to original and update the counter, reducing the counts of 2 and 4. The counter becomes counter 6, 1, 8, 1, 10, 1, 2 o'clock, 4 o'clock. Next, for number equals 4, we skip it because its count is 0. For number equals 6, we check if it and its pair, 6 plus k equals 8, are valid. Both are available, so we add 6 plus k//2 equals 7 to original and update the counter again. The counter becomes counter 10, 1, 2 o'clock, 4 o'clock, 6 o'clock, 8 o'clock. We then skip number equals 8 and number equals 10 as their counts are 0 or they cannot form valid pairs. At this point, original contains 3, 7. With original equals 3, 7, we now have the final output for this example. The reconstructed original array is returned as 3, 7. Let's now explore a third example where nums is 1, 1, 3, 3, 5, 5. Once again, we start by sorting the array, which is already sorted as 1, 1, 3, 3, 5, 5. For this input, we try possible values of k. Using the third element and the first element, nums 2, nums 0, we calculate k as 3, 1 equals 2. This value of k will be validated to check if it can produce a valid original array. For k equals 2, we initialize the counter as counter 1, 2, 3, 2, 5, 2, and an empty list original. We start processing nums. For number equals 1, first occurrence, both it and its pair, 1 plus k equals 3, are available. We add 1 plus k // 2 equals 2 to original and update the counter, reducing the counts of 1 and 3. The counter becomes counter 5, 2, 1, 1, 3, 1. For number equals 1, second occurrence, the same check passes, so we add another 2 to original and update the counter again. The counter becomes counter 5, 2, 1 o'clock, 3 o'clock. For number equals 3, we skip it as its count is 0. For number equals 5, first occurrence, we check its pair 5 plus k equals 7, but 7 is unavailable in the counter. This means the pairing is invalid, so we cannot reconstruct a valid original array with this pairing. After processing all elements, the reconstructed original array is 2, 2. This is returned as the final output for this example. Through these examples, we've seen how sorting, calculating valid k-values, and validating pairs systematically allows us to recover the original array from nums. By following these steps, we can solve the problem effectively for different inputs. To evaluate the time complexity of the solution, let's break it down step by step. First, the array nums is sorted, which has a time complexity of O, n log n, where n is the length of the array. Next, we have an outer loop that iterates over possible values of k. This loop runs from I equals 1 to n, nums, 1, leading to O, n, iterations. For each iteration, we compute the candidate k as the difference between nums, I, and nums, 0, which is an O, 1, operation. Additionally, there's the is_valid_k function, which constructs a counter for the nums array, requiring O, n, time. Within this function, we iterate through the elements of nums to check and update the counter for each number and number plus k. This requires O, n, operations in the worst case, making a single call to is_valid_k have a time complexity of O, n. Now, considering the total combined time complexity, the outer loop can call the is_valid_k function up to O, n, times in the worst case. Since each call to is_valid_k takes O, n, time, the total complexity of the outer loop and is_valid_k together is O, n, *O, n, or O, n squared. When we account for the sorting operation, which is O, n log n, alongside the main loop and is_valid_k, the overall time complexity of the solution is O, n squared. Shifting to space complexity, the counter object used in is_valid_k stores the frequency of elements in nums, which requires O, n, space in the worst case. Additionally, the original array, which holds the recovered elements, also requires O, n, space in the worst case. Additionally, we consider auxiliary space requirements. If the sorting algorithm used is in place, the sorting operation requires O, log n, space. However, if the algorithm is not in place, it may require O, n, additional space. Beyond this, the temporary variables and function calls contribute O, 1, extra space. Combining all these factors, the overall space complexity is dominated by the counter and the original array, resulting in O, n, space complexity. When comparing this to a brute force approach, the naive method would involve trying all possible pairs of differences k and iterating through all subsets of nums to validate them. This would result in a much higher time complexity, potentially O, n cubed, or worse. Our optimized approach, on the other hand, reduces the complexity to O, n squared, by leveraging sorting and hashing through the counter to validate potential k values efficiently. Finally, we can analyze the trade-offs and best versus worst-case scenarios. While a brute force approach might use less space by avoiding the counter, it comes at the cost of much higher time complexity. The optimized solution strikes a balance, using O(n) space while maintaining O(n) squared time efficiency. In the best-case scenario, if a valid k is found early, such as during the first iteration of the outer loop, the algorithm can terminate early. However, since the sorting step still dominates, the best-case time complexity remains O(n) log n. In the worst case, the outer loop completes all O(n) iterations, and each call to is_valid_k processes O(n) elements, leading to O(n) squared time complexity. Mathematically, sorting dominates initially with O(n) log n, and the outer loop combined with is_valid_k dominates with O(n) squared. Therefore, the overall time complexity is O(n) squared, and the space complexity remains O(n), driven by the counter and original array. One of the most common mistakes in solving this problem is assuming that the value of k is known or can be arbitrarily guessed. The key challenge here is to deduce both the original array and k simultaneously. If you overlook this, your solution may fail to handle the problem comprehensively. Another common oversight is forgetting to sort the nums array at the beginning. Since the recovery process relies heavily on understanding the relationship between the smallest and largest elements, an unsorted array can lead to incorrect logic for determining k. Similarly, it's crucial to validate k properly. Not every positive difference is a valid k. You need to ensure that for every pair x plus k in the original array, the frequencies align with those in nums. Mishandling duplicate elements is another pitfall. If nums contains duplicates, it's essential to carefully track and decrement their frequencies to avoid reconstructing an invalid original array. Finally, inefficient pair matching can be problematic. While it might be tempting to try all possible k values naively, this can lead to time complexity issues, especially for larger input sizes, resulting in time limit exceeded errors. Now, from an interview perspective, the crux of this problem lies in deducing k by analyzing the differences between elements. Sorting nums is a powerful strategy here, as the smallest valid k can often be derived from consecutive elements. This problem also draws inspiration from common techniques like the two-pointer method or hash map frequency counting, both of which are widely used in array reconstruction problems. To solve it optimally, you should consider sorting the array and then employing either the two-pointer technique or hash map-based frequency validation to efficiently test candidate values for k. Be mindful of edge cases, like when the array is very short, contains many duplicates, or involves extreme values like very large or very small integers. Additionally, this problem relates to others in the LeetCode catalog. For instance, twosome shares the idea of finding pairs with specific properties, while threesome involves sorting and group matching. Problems like group anagrams also emphasize sorting and frequency-based analysis, and even more complex ones, like maximum path quality of a graph, involve reconstructing solutions based on combinatorial logic. There are a few alternative approaches to solving this problem. One option is using a hash map-based frequency validation method. Here, you would track the frequency of each element using a hash map and, for each candidate k, verify that every element x has a corresponding x plus k. While this approach is intuitive, it requires careful implementation to avoid double counting, and its complexity is approximately O(n) log n, due to the sorting and hash map lookups. Another effective strategy is the two-pointer approach. By sorting nums and using two pointers to find valid pairs, x plus k, you can increment the pointers based on whether the current difference matches k. While this method is also efficient, with O(n) log n complexity, it requires special attention to pointer movement and edge cases. Finally, there's the brute force approach, which involves trying all possible values of k by iterating through the differences between sorted elements. While this can work for small input sizes, its O(n) squared complexity makes it unsuitable for larger arrays. Each of these methods has its trade-offs, so it's important to choose the one that balances clarity and efficiency for the given constraints. Great work! To summarize, we solved problem number 2122 by leveraging sorting and hash maps to reverse engineer the original array. We discussed the time and space complexity and highlighted key takeaways, such as using frequency maps and edge case testing. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!